everyone, and welcome back. Today we're going to be continuing our adventure in intermediate statistics and discuss a series of tests that can be viewed as non-parametric alternatives to tests that you probably already know, such as the t-test and ANOVA test, and a couple others as well. All right, a couple of them, named Kruskal-Wallis, Conover. We'll also be talking about the Conover Iman test and also the Man-Whitney test as well. So let us get right into it. So what do all of these tests have in common? So all of these non-parametric tests are going to be dancing around the concepts of ranks. So what exactly is a rank? Well, we'll give you a few examples of how to find ranks of samples in just a moment. But the non-alternative hypotheses that we're going to be working with for the Kruskal-Wallis test and also the Man-Whitney is that the ranks of one population equals the ranks of another population. So what do we exactly mean when we say that the ranks of a population are equal? So let's assume that the population only has 3 points, just to make it a little bit more easier to see. And let's assume that we have a point here, a point here, and a point here. So let's assume that this is population 1. And let's assume that we have another population, let's call it P2, which has points here, here, and here. Now notice that I have stacked them directly on top of each other, so when they match in terms of value with respect to all of the values in this total population of 6, then we said that the ranks of all of them are equal to one another, right? So for example, we have 6 points, so we're going to have ranks 1, 2, 3, 4, 5, and 6, generally speaking, right? But notice that these two have the same exact rank, so do we assign rank 1 to the top or 1 to the bottom? Actually, we're not going to assign 1 or 2 to either. What we're actually going to do is we're going to average those two together to get a rank of 1.5. And then for the next 2 points, we're going to have obviously 3 and 4, and they're going to be ranked to 3.5. And then we're going to be looking at those particular values, and that's going to go to 5 and 6, which are going to tie into 5.5. So notice that each of these populations of size 3 will have the ranks 1.5, 3.5, and 5.5 for each of their 3 elements, and hence they are equal. Now, some people will say that these tests are synonymous to saying that the population distributions are equal to one another, and that's not necessarily true. But what is true is if these ranks are equal to one another, let's assume that this isn't exactly a symmetric distribution, but roughly it is slightly skewed. So what you could see here is like x bar 1 and x bar 2 would both be located at the same exact position, again, even if it's not in part of the set. But if you have another distribution of points, let's assume we have this point here, and this point here, and again equivalent ranks, let's assume here, here, and here. Notice again, even in this example, the averages, x bar 1 and x bar 2, would likely be somewhere located there. But notice that the variances of these sets are completely different, even though the ranks are equal in both of these examples, right? So equality of ranks does not necessarily imply equality of distribution, because the variances could be completely different even though the ranks match. But if the ranks do match, then what we have here is evidence that the averages are also equal as well. So if we, for example, look at the average rank of both of the sets, or the distribution of the ranks, for example, then we would have non-parametric evidence, because we're not assuming it's normally distributed, that the means would be equal. So this perspective obviously motivates the idea of a non-parametric alternative to T or Z paced tests that assume normality of distributions. So let us just formally state out a couple of the goals that we plan to aim in this discussion. So our goal is to find non-parametric alternatives to the following test, and most of these you definitely should already know. So the first is going to be a T or Z test for 2 different means, and we're actually going to be talking about 2 non-parametric versions of this. The first is going to be called the Man-Whitney test, and there's another known as the Conover Iman test. Right? So those will be non-parametric alternatives for the t-test for 2 means. And then we also have the ANOVA tests for 3 or more means, right? And the test that we're going to be using for that in the non-parametric world will be the Kruskal-Wallis. And then, so that covers pretty much all of the values of means. And then we have, for example, the f-test for 2 variances, right? So we're going to be looking at how we can actually use ranks for testing equality of variances, which obviously equality of ranks doesn't imply equality of variances, but we have a couple alternative ways to sort of solve that problem too. And we also have, for example, the generalization of the f-test, which is, of course, the Bartlett test. If you've heard of the other alternatives compared to the Bartlett test, where you have slight variations from normality, then actually these tests will be a little bit more useful. And this is going to be for 3 plus variances, of course. And the test that we're actually going to use for both of these is known as the Conover. Some people will also call it the squared ranks test. Right? So we have 4 different tests that we plan to cover today. The Man-Whitney, the Conover Iman, Kruskal-Wallis, and Conover test, right? So let us just jump right into a numerical computational example and sort of see how we're going to work out these calculations and interpret them. So let's start with the basic case where we have 2 sets. I've made the sets relatively small and the numbers relatively nice because otherwise you'd probably be using R or some other statistical software in order to analyze this. And in R it's actually not that difficult to implement as well, but we can talk about that at another time. So let's assume that we have these 2 sets, S1 and S2, that have the elements 5, 7, 8, 9, 10, and 12, 6, 9, 13, 14, 15, 15, and 17 respectively. So what we want to do, or aim to do, is do a non-parametric alternative for the equality of 2 means test, which is obviously going to go into either a Man-Whitney or a Conover Iman, depending on your preference. Both relatively give the same results, but you should be analyzing both results and sort of analyze the distribution respectively on your own. But regardless of which test you're going to do, they're all going to start off relatively the same exact way. So what we're going to do is we're going to look at all of the ranks for these sets globally, right? So some people will call these the global ranks. So we're obviously going to have how many values here? So for the first sample, we have 1, 2, 3, 4, 5, and 6. So n1 will be equal to 6. And then we have 1, 2, 3, 4, 5, 6, and 7 values for the second element. So once we add up those 2 total, we're going to have a total of n is equal to 13 values, right? So what we're going to do is we're going to have global ranks 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. And in the end, if we have any ties, which we do have a couple in this particular data set, we have a couple 9s repeated, a couple 15s repeated at least, then some of these values might not be used, and we might be using decimals, or if we have a tie of 3, then we might be using one of these 3 times, or something like that. So let's look at the values in each of these sets, right? So where's the least value in these sets, right? So obviously if you want to do this by hand, sorting them from least to greatest is definitely a must, right? And also let's keep track of the sets, either 1 or 2, that these values belong to, right? So what are we going to do? So let's actually make this table a little bit more nicer to look at so it's a little bit more easily readable. Right? So what is the least value here? So we have obviously a 5, right? So that's going to be the first value, and that belongs to set number 1. The next value in the sequence is going to be this number 6, and that's going to be in set number 2. And then is going to come this 7 here, and that's going to be belonging to set number 1. And then we have 8, that's also going to be belonging to set number 1. And then we have 2 9s, so 9 and 9, and that belongs to set 1 and set 2, or you could do set 2 and 1. Now, since we have a tie for these 2, we don't want to assign set 1 to rank 5 and set 2 to rank 6. That's kind of biased, right? So what we're going to do is we're going to do the average of these 2, and that's going to give us a rank of 5.5 and 5.5 for each of them. And obviously, now they have the same exact rank in the global settings, right? Now let's continue. So the next value after 9 is obviously going to be 10, and that's going to belong to set number 1. And then we're going to have 12, and that's also going to be belonging to set number 1. And the rest of these values are going to be belonging to set number 2, so that's an obvious thing. So obviously going to have 13, 14, 15, 15, and 17. And of course we have another tie down here between ranks 11 and 12. Even though they belong to the same set, you still need to break those ties. So we're obviously going to have 11.5 and 11.5 for those two values, right? And obviously 11 plus 12 and 11.5 times 2 still add up to the same total rank, so we're not going to have any issues in that regard. So once you have this global rank table, now what you need to do is place these values of set number 1, for example, into a set of their own, and then we're going to have another set for the rank 2 the set 2 ranks, right? So what are we going to have? So the set of ranks for sample 1 are going to be what? So we're going to have rank 1, rank 3, rank 4, rank 5.5, and then rank 7, and then rank 8. So all I'm doing here is I'm just grabbing those values for the ranks, right? So 1, 3, 4, 5.5, 7, and 8. So those are the ranks for set number 1, and then we're also going to do it for set number 2, and that's going to be obviously everything that's not circled here. So 2, 5.5, 9, 10, 11.5, 11.5, and finally 13, right? So these two sets are going to be very, very important for setting up a lot of these statistical metrics that we're going to be working with for testing that previously mentioned hypothesis. So now let's talk through a couple of the metrics that we need for a Man-Whitney test. Okay, so let's assume that the size of S1 is N1. Let's assume that the size of S2 is equal to N2, and technically speaking, you could have several different samples. Let's assume we have G groups here, and let's assume that's equal to NG. And let's also denote that the sum from I is equal to 1 to G of each of those, let's define the total sample size across all groups to be equal to N. And obviously that's going to be the cardinality of S1 union S2 union all the way down to the union with SG. Okay, so the next metric that we need to calculate is referred to as the total ranks. The total ranks. So the total rank is going to be defined as follows, and I'm going to use capital T to denote it, and that's going to be equal to the sum from I is equal to 1 to NJ of the ranks of those particular groups. So the ranks in set J, each of them. Right? So we're going to take all of the values in R1 and we're going to add them together. We're going to take all the values in R2 and add them together. So if you sort of continue with the previous example that we have with our data sets, what you're actually going to find for T1 and T2, you're going to have a total of 28.5 and 62.5. And you're thinking, oh, well, we have T2 being significantly larger than T1. So does that imply that S2, the sample 2, is significantly greater than the majority of the values in T1? And you might be right when you say that, but keep in mind, sample 2 has more values than sample 1. So is it possible that T2 is larger only because of the larger sample? We don't know. Right, so let's sort of think about how we're going to work out those complicated details. Right, so let's assume that we have a rank of 1, and then followed by a rank of 2 in the next sample, and then 3, and then 4, and then 5, and then 6, and then 7, and then 8. So pretty much what you have here is like when you interlock your fingers one after the other, right? So all of the ranks are obviously not equal to each other in this particular demonstration, but they're roughly the same exact distribution, one could say. Right, so obviously we don't expect T1 and T2 to be equal to each other, even when we do have a relatively ideal scenario as this, where you have two sets that are not equal to each other, but they roughly have the same exact ranks to one another. So what we have here in this pedagogical example is T1 to be equal to 9 and T2 to be equal to 12. So obviously in this particular example, this is something that we might want to classify as statistically similar or statistically close to one another, right? But that obviously depends, because if I have more values in this particular set, for example, if I add another value here, another value here, and another value here, T2 is obviously going to dominate because it has more values in it compared to the other sample, right? So let's just take a moment and note that down, right? So if a set has more values in it, its total rank, so its rank total Tj, may be larger due to the larger sample size, right? And that can be a problem, right? And so it's larger due to its sample size, not necessarily its ranks, right? So here's a question that I want you to think about. You might want to pause the video and think about this, is how large can Tj of those total ranks actually be? So if you think about it from some things from pre-calculus, let's just recall one very cute identity. If I take the numbers 1, 2, 3, 4, and go all the way up to n, this is actually equal to n times n plus 1 divided by 2. It's a nice, very well-known arithmetic series, right? So, for example, if n is equal to 13, for our particular example, which was decomposed into a 6 plus 7 split for n1 and n2, then what you're actually going to have, if I total up all of the ranks for the total set of 13, what you're going to have is that T1 plus T2 for sample 1 and sample 2 is actually going to be equal to the total of the original ranks if we were to just unionize them into the same exact sample. So that would just be equal to 13 times 14 over 2, which is equal to 91. So for a 6-7 split for two sample analysis for equality of ranks, the upper bound for both T1 and T2 is equal to 91. And I leave it for you to verify that if we take 28.5 and 62.5 and add them together, you should get 91, right? So obviously we have this kind of issue, right? Because we don't want them to be relatively small, and we don't want these t's to be relatively large, even if they do have larger sample sizes. So is 62.5 significantly close to 91, and is 28.5 significantly close to 0? So we have two equivalent perspectives of the same exact problem. So how are we going to deal with the issue where our sample sizes might overtake the value of t, right? So if the ranks are about equal, the rank total should be about equal as well. So with this idea, some people will create these new test statistics, which I'm going to be calling U1 and U2, to be equal to the values T1 and T2, but trying to offset the sample size difference between the two, right? So if N2 is really large, when we subtract this total N2 value off, it pretty much brings that value of T2 down, and we're just going to call that N2, right? So we have these U test statistics, sometimes referred to as partial U test statistics, right? And for our example, if you're still following these calculations, you're going to find that U1 is equal to 7.5 and U2 is equal to 34.5. And we still see that the second sample has a test statistic that is significantly large, right? So now we need to figure out how large is large and how small is small when it comes to these values of U1 and U2. So now let's talk a little bit of statistical theory, and you might want to try and prove these things on your own, depending on what you're trying to get out of this conversation. But there is one very important theorem And you can take this as axiomatic, if you will, and it's that these values, uj, u1, and u2, will always be between 0. So even though we're subtracting something off, it will never result in a negative number. And the upper bound will actually be the product of the sample sizes. So that will be the largest value that u1 and u2 can be. And there's another very fun exercise if you want to try and prove some of these results, and that is if you take u1 and u2 and add them together, you're actually also going to get n1 times n2. And that's actually quite interesting. And obviously these might be just cute little mathematical facts, but it gives us some idea of how to quantify how large is large and how small is small. Now, we don't necessarily know, at least blindly, what the distribution of these u values are. So let's just call this the uj axis, and this, for example, the probability mass function of u. And we don't necessarily know what its value is, so we can just draw some arbitrary shape there. But obviously we don't want u1 or u2 to be close to 0, and we don't want u1 and u2 to be close to the maximum value that they can be, in particular the product of the two. So obviously our rejection region for equality of ranks will be on the opposite tails of this distribution, where the lower bound of this distribution is 0, and the upper bound of this is going to be n1 times n2. Right? So for our particular example, we actually have these cutoffs. We have 7.5 as the lower bound, and we have 34.5 in this particular value. Right? Now keep in mind that these are test statistics. Therefore, this shaded area in blue, do you know what the shaded area of blue is called? This is commonly called our p-value associated to our statistical test. Now, obviously, one can say, okay, well, I have our test statistics. How do I construct critical values to compare them to? And also, how do I calculate the p-value? Because I don't necessarily know what this distribution is in order to integrate it or do maybe a cumulative probability mass sum on that. Right? So let's sort of go ahead and answer that question for us. So what to compare these values to, in particular these test statistics, right? Because these are partial U test statistics. So in the R programming language, and Python and a couple others also have ways to calculate these critical values. These are associated to a distribution known as the Wilcoxon distribution, right? And in R, that would be QWILCOX. And if we're working with a two-tailed test, then obviously it's going to be alpha over 2. And then it's going to ask for your sample sizes, n1 and n2, and they can be inputted in any order. And then we can do lower dot tail is equal to true, or you could do lower tail is equal to false, depending on the values that you actually want to get, right? And these are going to give you critical values associated to your distribution. You can call it, say, U crit L and U crit W to compare to U stat L and U stat R, for example. Right? So if we choose, for example, alpha is equal to 0.05, which a lot of people do, what you're actually going to get is a Wilcoxon critical value on the left to be equal to 7, and a Wilcoxon critical value on the right to be equal to 35. Right? So where are these values in this table? So let's draw this in orange. So 7 is going to be located here, and 35 is going to be located above there, just the 35. So if we sort of shade this in, right, so what would this area be? So this area is shaded in red. That's our alpha over 2, and that's our alpha over 2 here. And keep in mind, how do we get these two values? You just switch the true to false or false to true, whichever one you did first, right? And using a similar function, instead of Q, just replace that with P and feed it those associated test statistics, you can also find that the associated P value, which according to this picture obviously should be larger than our alpha value, is actually going to come out to approximately 0.0514. Now, if you chose alpha and then you find the P value, obviously our P value is larger, so we fail to reject the null hypothesis, at least slightly, with some weak evidence. But if you calculate the critical values compared to your partial U stats, you get the same exact conclusion, right? And that's looking at things from two angles. Now, there is one very important thing you must note about this. So since one moves down, for example, when I talk about one, I'm talking about U1 or U2, the other will always move up. And why is that? Well, that's very easy to prove, because keep in mind U1 and U2 always add up to the product of N1 and N2. So if U1 gets smaller, U2 must get larger in order to still be equal to this product of the sample sizes, right? So as one moves up, the other moves down. So technically speaking, we should not be looking at a two-tailed test here, because we already know what the other tail is going to do when we already know what either the left or right tail looks like in terms of extremity. So what is common for the Mann-Whitney tests? So what the Mann-Whitney test does is it defines as the test statistic, instead of looking at both, it actually just looks at the minimum of U1 and U2, right? And some people will use this instead as just U stat to be equal to the minimum of U1 and U2, and it just looks at the minimum of those partial U stats, and then instead of dividing your alpha over 2, it just looks at your alpha value in the left tail. So how small is close to 0? This critical value where it's just one-tailed will answer that for you, right? So that's pretty much how the Mann-Whitney test, the two-tailed version and the one-tailed version actually goes, right? So the Mann-Whitney, obviously since we're only looking at 2, is only used for 2 groups at a time, or you can use it for pairwise comparisons if you have multiple groups. But as you already know, pairwise comparisons does come with that downside, because every test you do, you're going to have a potential possibility of making a type 1 or type 2 error. So that's obviously where the Kruskal-Wallis is going to enter the story and sort of overcome that particular pairwise comparison issue, right? So let's actually look at how the Kruskal-Wallis test is set up, just in case you do have multiple groups and you don't want to do pairwise comparison tests. So now let us consider how we test the equality of ranks across multiple groups, in particular when G is greater than or equal to 3. Because if G was equal to 2, then you should be using a Mann-Whitney test, for example, right? So keep in mind the alternative is that the ranks for at least 2 samples are significantly different from each other. So even if you have 50 groups and 48 of them are really similar to each other, if one of the other 2 are not similar to each other, then this is going to lead to a rejection, right? And then obviously if it leads into a rejection, you can do pairwise comparison test as a post hoc test to sort of figure out which ones are significantly different from each other, right? So how does the Kruskal-Wallis test go? All right, so Kruskal-Wallis, so this is pretty much your non-parametric ANOVA test, is going to start off in the following way. So we have our sample 1, our sample 2, all the way down to sample G now. Again, G greater than or equal to 3. We're going to globalize rank all of its values, and then we're going to have sets R1, R2, all the way down to a set of ranks, RG. And for each of those sets of ranks, we're also going to have average ranks for those sets, right? So we're going to have a bunch of ranked sets, and we're going to have average rank sets as well, right? Also keep in mind, if we have S that is defined to be S1 union S2 union all the way down to union SG, where the cardinality of S is equal to N, and we look at all of the ranks in that particular sample. I leave this as an exercise because this is actually really pretty fun to prove. This is always actually equal to m plus 1 divided by 2, right? So this is a very useful thing to keep in mind, that the average rank across all values, even if you use ties, is always equal to m plus 1. And this is a very, very important thing to keep in mind because it actually allows you to shortcut a lot of these calculations. And instead of using r bar, I'm going to use r bar because it's technically the grand mean of ranks, which is what I'm going to call it, right? So how does the Kruskal-Wallis test statistic look like? So the Kruskal-Wallis stat, some people will use H instead, but I'm just going to use KW for Kruskal-Wallis because H is commonly used for something else. The Kruskal-Wallis stat is going to be defined as follows. So it's going to be n minus 1 times a fraction of sums, right? So on the top, we're going to have the sum from j is equal to 1 to g of nj times the average rank of group j minus the grand rank squared. Now, if you're familiar with the ANOVA test for parametric testing that assumes normality, this is similar to the SSM in the ANOVA test. The only difference is you replace r bar j with x bar j and r bar bar with x bar bar, and you get the SSM for your ANOVA test. And on the bottom, where we're going to have here is the sum from j is equal to 1 to g of the sum from I is equal to 1 to nj of r, I, j, the baby ranks of each of the groups, minus the grand average squared. Now, some people will look at this as the average of group J, but the Kruskal-Wallis in its original form uses the grand rank to compare. But nonetheless, this object here is also similar to the SSE if r bar bar was changed to r bar j, right? But nonetheless, there are similarities between both the original form and that slight variation if we were to change that slight character, right? Now, one very beautiful thing about this is we don't actually have to use the Wilcoxon distribution to get critical values, because as each of these n's, if each of them are significantly large, then what you're actually going to see, and some people will use 5 and 10 as cutoffs, but technically speaking, it really depends on the scenario. This test statistic is actually going to follow a chi-squared distribution with g minus 1 degrees of freedom, right? So that's a distribution that we know very well, and one can find, at least for our example, in case you're trying to calculate this, our KW stat for our two groups, even though technically you're not supposed to be using KW for two groups, is going to be approximately equal to 3.74 if you want to just try and work that out on your own, right? So is 3.74 large or small? Well, it depends. Obviously, we need to look at a chi-squared distribution. So generally speaking, as long as g is not equal to 2, which it is in this case, is going to look more like this. And obviously, this is going to be a right-tailed test, so your alpha is always going to be in the right-tailed area. And this value here, chi-squared crit, is going to be what you're going to be comparing this KW stat to in this particular case. And keep in mind, this is a chi-squared g minus 1 distribution. And I believe when g is equal to 2, when the degrees of freedom is equal to 1, you have a weird case where it sort of looks like an exponential decay curve, which is why this shape is slightly misleading when g is equal to 2, because technically you're not supposed to be using it for g is equal to 2 anyway. But for our particular example, if we do use g is equal to 2, and that's perfectly okay on the calculation m, with 1 degree of freedom, you're going to have 3.84 as your critical value, right? So we have 3.84 there. We have 3.74 over here. So we're not in the rejection region, so we would fail to reject the null hypothesis that the ranks across all of these g equals to 2 groups are equal to each other, right? So that's actually very, very cool. Now, I just want to mention here, once you do have evidence to reject the null hypothesis under a Kruskal-Wallis, then you can use, for example, pairwise comparison tests with the Mann-Whitney test. But an alternative to Mann-Whitney for pairwise comparison or two-test is known as a Conover Iman test. Right? And the test statistic for Conover Iman is actually quite easy. So the Conover Iman, or the CI stat, is actually going to be defined to be T1 minus T2, so those are their total ranks, divided by the square root of n, our total sample size, times m plus 1 over 12, times 1 over n1 plus 1 over n2. Some people will put absolute values here, but theoretically, you're not supposed to. And the reason I say that is because this test statistic, if you leave off the absolute values, is going to follow a t distribution with n1 plus n2 minus 2 degrees of freedom. And if you take the absolute value, it can't follow a t distribution because t goes to negative infinity and absolute value does not. Right? And you might be looking at this and be like, oh, this bottom obviously would be the standard error of the difference between two ranks, but nonetheless this overall object is reminiscent of a pooled variance t-test, right? So this object here is sort of making us think, oh, is that the pooled ranks test? And I'll let you sort of think about that on your own and sort of see why that is. But if you know the formula for the standard error for the pooled variance t-test, this thing in parentheses definitely should look familiar, and also the degrees of freedom, all that, right? So the Conover Iman test is actually a little bit more quicker compared to a Man-Whitney test because, one, you don't have to do a Wilcoxon critical value, and all you need is the total ranks and the sub sample sizes to conduct this, right? And that's obviously convenient, right? So that gives us our Mann-Whitney, our Kruskal-Wallis, and this newly introduced Conover Iman test. And all of them assess the equality of ranks for means in the non-parametric manner. Now let's look at the non-parametric variation of the Bartlett test. So now we look at the non-parametric alternative to the Bartlett test. And the non-parametric alternative is called the Conover Squared ranks test. So how does the Conover test, and what is it and how should it be conducted, right? So what we're trying to look at now, we're still going to be looking at the ranks, but we're going to be looking at the spread of the ranks instead. And keep in mind, just because the ranks are equal does not mean that the spread of those ranks are equal as well. Right? So let us just recall the formula for sample variance or even population variance to sort of get an idea of a metric that we might want to construct. So the formula for the sample variance for a group J is going to be equal to the sum from I is equal to 1 to nj of the individual values xij belonging to group J minus the mean of that group squared, all divided by nj minus 1. So pretty much what it does is it takes each of the values and it shifts them about the mean, right? And then it squares that. So what we're actually going to do is we're going to do a very similar thing now, right? So keep in mind we have several groups now. We have S1, we have S2, and potentially we have more, in particular SG of them. And keep in mind the Conover test can be used for 2 or even more. Obviously, the larger the sample size, the better for this. So for each of these samples, what we're actually going to do is calculate some new metrics, so A1, A2, all the way down to AG, and these are going to be calculated as follows. So we're going to do the absolute value of the original set S1 minus the mean of X1, the original S2 values minus X2, and that's going to continue all the way down to the set G minus the average of set G. So it's pretty much doing the same exact thing as we did for the normal variances. So what we have here, these A's, these are just shifted absolute values. So these are just shifted absolute values. Nothing about ranks has been done yet. But once you have all of these values, A1 and A2 and A3, then what we're going to do is we're going to rank them globally. Rank them globally, just like we did R1 and R2 in terms of their construction. So once we rank them globally, what we're going to have is we're going to have SR1 SR2 all the way down to SRG, right? So these are our shifted absolute value ranks, right? So that's actually pretty interesting, right? So these are just the ranks. That's a horrible way of writing ranks, but it's the ranks of the AJ values globally. Okay? So once we have our shifted absolute value ranks, what we're going to do is we're going to calculate a couple metrics. So the first value I'm going to call the SSSRJ. Now, that's a long abbreviation, but what exactly is that? So I'm going to write down the formula here. So this is going to be the sum from I is equal to 1 to nj. So each group is going to have one of these. And it's going to be equal to SRJ, each of them squared. Right? So do you want to take a guess of what this SSSR stands for? So this is the sum of squared shifted ranks. So it's the sum of squared shifted ranks. So you can practice calculating this. So we're going to have an SSSR1 and an SSSR2 for our particular samples that we had in the beginning of 253.5 and 563.5 as well. So those are fun to implement on your own. Right? So once we have our sum of squared shifted ranks, then comes another metric, which I'm going to abbreviate by PSSR or PSSSR, right? So this is going to be just the pooled sum of squared shifted ranks value. So P is just pulled here. And this is just going to be equal to SSSR1 plus SSSR2 all the way down to SSSRG all the way divided by M1 plus N2 all the way down to NG. But keep in mind the denominator for this is just going to be equal to M. But for our particular example, that's going to come out to approximately 62.85. Again, that's actually not a hard metric to calculate. The next metric that we're going to calculate is called the Conover V metric, which is going to then be used to calculate the Conover test statistic. And this is slightly complicated at first, but let's sort of work with it on our own. So this is going to be equal to 1 over n minus 1 times, big bracket here, and this is going to be the sum from I is equal to 1 to n. So it's the original values from our original shifted ranks. So this is going to be SRI squared, right? So remember when we took all of our values and we subtracted the average, and then we took the absolute value, put them all in a set, square them all, and add them all. That's what this particular sum is equal to. And once we're done with that, so keep in mind that is an entity, we're then going to be subtracting off the total sample size, n1 plus n2 all the way down to ng, and multiply it by our PSSR value, and then we're going to square it. Right? And once we do that, for our particular example, you're going to get 3,100, 14, and 68, just to make sure you're calculating everything correctly. Now, we have one more step, and then we are done. And you might be thinking, wow, this is really complicated. Why would anybody come up with this? And that's the actual beauty of the Conover test, and I'll illustrate that and why in just a moment. So our final value, CO, that's our Conover test statistic, will be equal to 1 over capital V, this value V here, right? So the Conover V, and that's going to be multiplied by, again, big sum. So we're going to do the sum from J is equal to 1 to G. So we're going to do this for each of our groups. So we're going to have SSSR, and then we're going to do the J values, and then we're going to square each of them, divide that squared SSSR value by the sample size, and that's going to give us some number, and we do that for each of our groups. And then keep in mind that's one value that you need to calculate, and then you're going to subtract that from n times our PSSSR value, again squared again. And once you calculate that, that's going to be approximately equal to 1.5176. So it's actually a quite very friendly looking number. right? So you might be thinking, okay, a Conover test statistic of 1.5, is that large or is that small? Well, is there a Conover distribution? Maybe, maybe not. But why did Conover want to build it in this very complicated way? So what they're trying to do is build this into a distribution that we already know, and as long as the sample sizes are relatively large, this Conover test statistic will also follow a chi-squared g minus 1 distribution, just like the Kruskal-Wallis test statistic. And that's actually very, very beautiful. So whatever we compared our Kruskal-Wallis test statistic to before, that's also what you're going to be comparing this Conover test statistic to in order to see where you have evidence to believe that the variances are significantly different or similar to one another in terms of their spread rather than their measure of central tendency. Right? So those are all of your non-parametric common tests for the ANOVA test, t-test, and the F and Bartlett test as well. I hope you enjoyed this video, and I'll see you in the next one. Take care.